A company just started taking pre-orders for a $20,000 home robot that claims to be autonomous, but there's a major problem: nothing shown in their demos actually works without human control. Meanwhile, two genuinely impressive robotics breakthroughs just happened that deserve your attention. Let me show you what's real and what's marketing hype. 1X Technologies just unveiled the 1X Neo robot, positioning it as a humanoid assistant designed specifically for home use. The company claims it can automate everyday chores and provide personalized assistance around your house. The promotional materials show it performing tasks like opening doors, carrying items, turning lights on and off, folding clothes, and loading dishwashers. The pricing model offers two options: purchase for $20,000 outright or subscribe at $500 per month. Pre-orders are currently open with planned delivery by next year. On the surface, this sounds like consumer robotics finally arriving for home use. However, there's a significant disconnect between the marketing claims and the actual capabilities. A Wall Street Journal reporter who investigated the demonstrations revealed that everything filmed relies heavily on remote teleoperation by a human operator. Every single task shown in the promotional videos, folding clothes, opening doors, loading the dishwasher, was actually controlled by a person using a VR headset and controllers. The reporter documented several critical limitations. Neo struggles to perform even basic tasks independently. Simple chores take an extremely long time to complete. The robot nearly falls over during operation, suggesting balance and stability issues. Most importantly, there's minimal evidence that this robot can work independently in a home environment without constant human control. This raises serious concerns about the product announcement. The company is accepting pre-orders for a $20,000 robot, while unable to demonstrate the autonomous capabilities they're advertising. The gap between claimed functionality and actual performance is substantial enough to question whether this announcement is premature. For consumers considering pre-ordering, the reality is that you would essentially be purchasing a very expensive remotely operated machine rather than an autonomous home assistant. The technology appears to be nowhere near ready for independent home use, despite the marketing suggesting otherwise. Now let's look at something genuinely impressive. The Unitree G1 robot, which weighs only 35 kilograms, successfully pulled a 1,400 kilogram car. This demonstration showcases real autonomous capability rather than remote operation. The robot was trained using an algorithm from a research paper called THOR, which stands for Towards Human Level Whole Body Reactions. The training focused on full body coordination and dynamic movement adaptation. What makes this demonstration notable is how the robot adjusts its posture to maximize pulling efficiency. It uses its entire body weight and strength strategically, optimizing the friction between its feet and the ground. The robot continuously adapts its movements throughout the pulling process, responding to the changing forces and maintaining balance. From a physics perspective, pulling a wheeled car in neutral gear reduces the actual force required compared to lifting 1,400 kilograms directly. The wheels significantly decrease resistance. However, the impressive aspect isn't the raw strength but rather the sophisticated full-body coordination required to execute this task. The robot must calculate optimal body positioning, maintain balance while applying force, adjust to feedback in real time, and coordinate multiple joints and actuators simultaneously. This level of whole-body control represents genuine advancement in robotics capabilities. The THOR algorithm that enables this behavior demonstrates progress toward robots that can handle dynamic, physically demanding tasks autonomously. This has practical applications for industrial settings, logistics operations, and eventually home environments where robots need to manipulate heavy or awkward objects. Leisure Robotics introduced the Kuavo 5, a humanoid robot featuring some interesting design innovations. The standout feature is its modular limb system. You can swap the robot's legs between feet for walking and wheels for rolling depending on the task requirements. The specifications include a battery life exceeding 8 hours and a maximum load capacity of 20 kilograms. These are practical numbers for real-world deployment rather than just laboratory demonstrations. Originally developed for industrial applications like assembly lines, logistics operations, and manufacturing environments, Kuavo 5 is now being adapted for home use as well. This industrial-to-consumer pathway often produces more robust products since the technology was initially designed for demanding commercial environments. The robot integrates Huawei's Pangu model as its artificial intelligence system. This AI serves as the robot's decision-making brain, handling perception of the environment, planning actions, and controlling movements. Having sophisticated AI integrated directly into the robot rather than relying on cloud processing can enable faster response times and more reliable operation. The modular design philosophy addresses a key challenge in robotics. Different environments and tasks require different mobility solutions. Feet work better for stairs and uneven terrain, while wheels are more efficient for flat surfaces and speed. A robot that can adapt its locomotion method expands its practical usefulness significantly. ByteDance released GameTars, an AI agent that represents a fundamentally different approach to game playing AI. Unlike previous systems that required specific programming for each game, GameTars plays video games using only the inputs a human player would have: visual information from the screen and keyboard and mouse controls. The system observes gameplay visuals, analyzes what's happening, thinks through strategies, plans actions, and executes keyboard and mouse inputs. All of these functions operate within a single integrated model rather than separate specialized systems. After training on extensive video game data, GameTars learn to play games autonomously without prior knowledge of specific rules. The AI figures out game mechanics, objectives, and strategies through observation and experimentation, similar to how humans learn new games. The performance is impressive and operates in real time. The system processes visual and text information from the game, makes decisions, and executes controls fast enough to play competitively. This lightweight efficiency makes it practical rather than just a research demonstration. Benchmark results show GameTars outperforming GPT-4 and other leading models across multiple game genres. It excels in open-world tasks in Minecraft, first-person shooter games, web-based games, and various simulator games. These benchmarks demonstrate versatility across very different game types and mechanics. The real value emerges when you watch GameTars encounter games it has never seen during training. The AI explores the environment, experiments with controls, observes consequences, and gradually develops effective strategies. This works across racing games, flight simulators, and shooters like Doom. The generalization capability is the key breakthrough. The implications extend far beyond gaming. This technology directly translates to real-world robotics applications. Imagine a humanoid robot encountering a task it has never performed before. Traditional systems would fail because the specific situation wasn't in the training data. This represents a pathway toward robots that can truly adapt to real-world complexity and variability rather than only functioning in controlled, predictable environments. The gaming application serves as a test bed for developing capabilities that will eventually power practical autonomous robots. If you want to stay updated on real robotics breakthroughs and honest assessments of new AI technologies, subscribe to the channel. All the research papers and technical links are in the description below. Thanks for watching, and I'll see you in the next video.